Hello. In this video, we're going to look at continuity part 2. So more examples of what it means to be continuous and how to determine when a function is or isn't continuous. So let's look at this function fx. It's going to be a piecewise function, but a more complicated version. So it's x squared minus 1 over x squared plus 2x minus 3 when x is less than 1. And it's 2 minus x over 2x when x is greater than or equal to 1. So let's first go ahead and look at the easier problem of determining the domain of fx. So to determine the domain, of course, there are a few questions. I might ask, what about x equals to 1? Is the function defined there? And it definitely is. When x is equal to 1, it's going to take this portion. So x equal to 1 is good. But what about x equal to maybe 2 or 3 or 0 or other numbers that might be of an issue? And of course, if you look at the bottom of this, of course, there could be zeros. Or if you look at the bottom of this, yeah, we definitely could get a 0 from there. And if you have a 0 in the denominator, you get undefined. So I think the second one is easier here. Definitely, we would have a problem at x equal to 0 there. So I'm going to put x equal to 0, but I'm going to put a question mark just next to it for right now. And then I'm going to go ahead and look here and try to factor. So two numbers that multiply to give negative 3, add to give 2, x minus 1, x plus 3. So then that gives me x equal to 1, x equal to negative 3. So x equal to 1 question mark, x equal to negative 3. Now let's go through these one at a time. If I were to plug in 0 into the bottom of this, I would get undefined. But the thing is that when x is equal to 0, I don't actually use this portion of the piecewise function. It's kind of sneaky. When x is equal to 0, 0 is less than 1, I use this portion. And so f of 0 is equal to 0 squared minus 1 over 0 squared plus 2 times 0 minus 3, which is equal to negative 1 over negative 3, which is just 1/3. So this is actually defined. When x is equal to 0, we're good, because we're not actually looking at this portion of the function. Let's see what happens when x is equal to 1. Well, when x is equal to 1, although you couldn't divide this portion by 0 with an x equal to 1, it's supposed to actually take this portion. X is equal to 1, so we take this portion of the function. Again, kind of sneaky. F of 1 is equal to 2 minus 1 over 2 times 1, which is going to be 1 over 2. And so x equal to 1 also works. How about x equal to negative 3? Well, that looks like an issue, because for negative 3, it's going to be less than 1, so it is going to be this portion, and it's not going to plug in. So f of negative 3, this is undefined. But the other ones are defined. They're good to go. So our answer for the domain is going to be negative infinity to negative 3, union negative 3 to infinity. Now let's go ahead and find where the function is continuous. First off, we should check x equal to 1. That's going to be our main place where we would check something, because x equal to 1 is where we have the handoff between the two functions. So if we check x equal to 1, let's see what we get for, we'll do it over here, see what we get for the two sides. So when you do x equal to 1, we have to find f of 1. That's step 1. F of 1 is equal to 1/2. Step 2, we need to do the limit as x approaches 1 from the left. When we do 1 from the left, we're going to get the top function, and I'm going to factor that difference of squares in the top. So x minus 1, x plus 1 over x minus 1, x plus 3. Now, if you were to just plug it in right here, you would see that you get 0, because there's a 0 here, over 0. So this is actually do more work. This limit requires us to do some more work, but thankfully we've been doing the factoring as we go, and so the work that we need to do is just a simple cancellation. So limit x approaches 1 from the left of x plus 1 over x plus 3. Looks like we can plug it in now. We're going to get 2 over 4, which is 1/2. Okay, let's go ahead and do the limit x approaches 1 from the right. That's going to be 2 minus x over 2x. So it'll be 2 minus 1, which is 1 over 2. And these two are equal. So therefore, the limit as x approaches 1 of f of x, it exists and it equals a half. Finally, part 3, the limit x approaches 1 of f of x, which is a half, clearly equals f of 1, which is also a half. And so we get, therefore, fx is continuous at x equal to 1. So let's go ahead and summarize what we found then, because we had rational functions and we have the domain. So we can say that since, well, those two rational functions, x squared minus 1 over x squared plus 2x minus 3 and 2 minus x over 2x are rational functions, which are, of course, continuous. F of x is continuous on negative infinity to negative 3 union negative 3 to infinity. Again, we get the function being continuous over its whole domain because the one little point that we thought might have an issue at x equals 1 turned out to not have an issue, and the other parts are just rational functions, so they're good to go. Let's go ahead and do another example here. So here we have f of x equal to x squared plus x over x, 2 or sine x over x when x is less than 0, greater than 0, or equal to 0. Is this continuous at x equals to 0? Well, let's go ahead and do step number 1. In this case, we have to find f of 0, which is a little bizarre because normally it's just greater than or equal to or less than or equal to, but in this case, they've told you specifically. When x is less than 0, it's this thing. When x is greater than 0, it's this thing. But when it's 0, when it's identically 0, give it the value 2. So f of 0 is 2. Okay, let's go ahead and do some limits. Limit x approaches 0 from the left, x squared plus x over x. Now we've got to do some work here because this is going to give 0 over 0. And it looks like some factoring is going to be in order. So x factors out, x plus 1, x plus 1 over x. Cancel out those x's. And we'll get the limit x approaches 0 from the left of x plus 1, which of course is just equal to 1. Now we go ahead and do the limit as x approaches 0 from the right, which will be sine x over x. And remember, this is a special limit. So we're allowed, of course we know sine of 0 is 0, so this is 0 over 0, there's a do more work, but the work we can do is just write 1, because it's a special limit. Well, notice, these are equal. So therefore, the limit as x approaches 0 of f of x, it exists and it equals 1. But we're not done, and this is why we have to write step 3. You might have been feeling like step 3 was a bit of unnecessary work, it was a bit extra. Why do you have this step 3? It doesn't seem to be important. Well, this is why. The limit as x approaches 0 of f of x is equal to 1, which is not equal to f of 0. Because if you notice up here, f of 0 is 2. And so in this case, the function is not equal to its limit. So we have to say, therefore, f of x is not continuous at x equal to 0. And so it doesn't come up too often that third step is important, but when it does come up, it's very important. That third essential check is there to make sure that the limit and the function are actually the same thing. Now let's go ahead and do some of my favorite problems, the ones where we have some missing letters. So here we have fx equal to c squared x when x is less than 1, or cx plus 2 if x is greater than or equal to 1. And so let's see, can we find an answer to this? Can we solve this? Could we determine the values of c so that f of x is continuous? C is unknown and we want to figure out what we should make c. so that it's continuous. Now just for fun, I'm going to investigate this on Desmos first. Let's see what we get on Desmos. So here we have our Desmos. We type it in just like we see it. And Desmos is actually very helpful. It will say, do you want a slider? And of course we do. We want a slider. We want to find out what that value of c is. So let's go ahead and play with the value of c. Currently the function is not continuous. But if we move it over, oh, it's not continuous there. But did you see that for a moment? Maybe right here, it looks like if we zero in on that value of c at c equals to 2, it looks like that's the perfect value so that the two graphs line up and we get a continuous function. So maybe we think the answer is c equals to 2. Let's see if we can prove that algebraically. So we're going to go ahead and investigate at x equal to 1. And in particular, we're going to start with the limit here. So the limit x approaches 1 from the left. That'll be c squared x. Now again, be careful here. We're plugging in for x, not c. C is a constant. So the constant just remains, but we plug in for the x as 1. So the limit will be c squared. Let's go ahead and do the limit as x approaches 1 from the right of cx plus 2. Again, we only plug in for the x, so this will be c times 1 plus 2, which is c plus 2. Now normally at this step, we would say that these two are equal. But in this case, well, they're not equal. One is c squared and one is c plus 2. So what we can say is we want them to be equal. Because normally we would say these two are equal and we go ahead and say the limit exists, the function is continuous. In this case though, we can only say we want them to be equal. So what we're saying really is for fx to be continuous at x equals to 0, or x equals to 1, we want these to be equal. And how do you set two things equal if you want them to be equal in math? If we want these equal, well, we literally just make an equation. For fx to be continuous, we just write c squared equal to c plus 2. Now this is like a pre-calculus question. We can go ahead and move the c and the 2 over to the other side. We can do a little factoring here. So this will factor as c plus 1 and c minus 2. And that will give us c equal to negative 1 and c equal to 2. Well, this we found in Desmos, but what in the world is this negative 1? It appears like our Desmos investigation was maybe a little bit hasty. We've definitely showed that c equals to 2 will make the function continuous, but apparently so will c equals to negative 1. Let's go back to our graph. So we had the slider at 2 before and it was definitely continuous. And as you move the slider to the left, you'll see that the functions break up. But if you move it more left, you'll see that the functions start to come together again. And indeed, if you set c equal to negative 1, the functions are again continuous. There are actually multiple values for c, in this case 2 different values, that would make the functions continuous. And again, this is just a piece of caution. Calculators and Desmos and computers are very, very useful for doing mathematics. But you do need to do algebra as well, and you need to have a more logical approach, a more systematic approach, because sometimes using a calculator or a computer may cause you to become overconfident and actually miss a potential solution. So just be careful of that as you work on mathematics in the future. Now we're going to go ahead and do another example here. This one we're going to have 2 letters, A and B. And if you notice, there's 2 points we're going to investigate, x equal to 2 and x equal to 3. So I'm going to go ahead and do x equal to 2. So we have the limit, x approaches 2 from the left. Well, that means we're going to need the x squared minus 4 business over x minus 2. If I plug that in, I get 0 over 0, so I definitely think I should factor. X approaches 2 from the left of x minus 2, x plus 2 over x minus 2. Cancel out those factors. And I'm going to get just simply the limit as x approaches 2 from the left of x plus 2, which is 4. Now over here, I'm going to do the limit x approaches 2 from the right of, well, it'll be ax squared minus bx minus 3. Remember, we only plug in for the x, so it'll be a times 2 squared minus b times 2 minus 3. So 4a minus 2b minus 3. And so these two, we want these to be equal. So we want equal. So we could go ahead and set them equal to each other, and that would give us the following. 4 is equal to 4a minus 2b minus 3. So I guess you could maybe move that 3 to the other side and give 7 equals 4a minus 2b, but you're going to get a bit of a problem here. You can't isolate for a and b separately because you have two variables. You can't get what a is equal to without having a b mixed up in there. So this seems to be a bit of an issue. But no worries, go ahead and find x equal to 3. Go ahead and pause the video and see if you can see what happens when you investigate x equal to 3. So assuming you gave that a try, let's go ahead and do x equal to 3. So we would have the following. Limit x approaches 3 from the left. Means we're going to look at the ax squared minus bx minus 3. So that'll be 9a minus 3b minus 3. And then the limit x approaches 3 from the right of 2x minus a plus b. And that'll be equal to 6 minus a plus b. Well, that's good to go. We can set these equal. So set them equal. And that'll give us 9a minus 3b minus 3 is equal to 6 minus a plus b. I guess we could move some things over, so let's go ahead and move the letters to one side, the numbers to the other. So we'll take the a over here to give us a 10a. We'll take the b over here to give us a minus 4b. And then it will be equal to 9. So now we have another equation with two variables and we can't solve it. But if you have two equations with two unknowns, that is a thing you can solve in mathematics. So hopefully you remember how to solve a system of two equations. If not, we're going to go ahead and do an example here. But if this is a bit new to you and you don't really remember this, I'd encourage you to look up a video on solving a system of equations just to refresh your memory on how this works. So let's go ahead and give this a shot. We're going to use the method of substitution. So we're going to take here the equation that we had with the first one. We had 7 equal to 4a minus 2b. So I'm going to get 7 plus 2b equals 4a. So a is equal to 7 plus 2b over 4. And I'm going to take that and I'm going to plug it in to the other equation for the a. So 10, 7 plus 2b over 4 minus 4b is equal to 9. So we've got to get rid of that 4 eventually and multiply that 10. So that'll be 70 plus 20b over 4 minus 4b equals 9. We can go ahead and multiply everything by 4 to clear the 4. So that'll be times 4 times 4 times 4. 70 plus 20b minus 16b equal to 36. So next up we can go ahead and combine the b's. 4b, and we can move the 70 to the other side. That'll be negative 34. So divide by 4, divide by 4. b is equal to negative, well, we could reduce that 17 over 2. So there's our first number that we need. And usually the way we do this is we take our b value and we plug it back in over here to get the a value. So a is equal to 7 plus 2 times negative 17 over 2 all over 4. Well, the 2's cancel, so you get 7 minus 17 over 4. 7 minus 17 is going to be negative 10. And we could simplify that one more time to give us a is equal to negative 5 over 2. So those are our two values. Definitely took a lot of work on the side here. But again, this portion isn't technically calculus. This is pre-calculus. So make sure you review this section here. It doesn't really have to do with limits. It's more solving equations. Definitely an important skill, but this isn't really to do with limits. So just make sure that you can handle this stuff. Of course, if you have questions, feel free to ask me, and we can always do a few more examples on these. So let's do a quick clicker question here. What value of c makes this function continuous? So we have our piecewise function, x is less than or equal to 2 or greater than 2. What value of c would we need here? I encourage you to pause the video and give this one a try. All right, so when we do the limit, x approaches 2 from the left of cx plus 5, we're going to get 2c plus 5. When we do the limit as x approaches 2 from the right of cx squared minus 7, we're going to get 4c minus 7. So we set those equal to each other. 2c plus 5 equals 4c minus 7. Move the 2c to the right-hand side, so that will be 12 equals 2c, and so c is equal to 6. So the answer is, well, c equal to 6. So for homework, go ahead and try the continuity worksheet. As well, you can try a few questions in the textbook, 39, 40, and 46. And as always, thanks for watching.